Yes, roll number 63.
Namaste.
Yes, sir.
Double करो.
सावली तिथे इथं.
You want to start, sir?
Yes, sir, yes.
Yes, respected chairperson, program coordinator, dear colleagues, I'm roll number 63, Assistant Professor Ganesh Navandar from Khasdar Govindra Adik Law College, Sri Rampur. It is my privilege to introduce our today's esteemed resource person, Professor Dr. Babasaheb Nivrutti Dole, sir, a senior academician and research in the discipline of physics. He is presently serving professor and head of department of physics of Dr. Babasaheb Ambedkar Marathwada University, Chhatrapati Sambhajinagar. Dr. Dole sir obtained his doctoral degree in solid state physics in 2002 and possesses more than 2 decades of postgraduate teaching and research experience.
So, roll number 63 आपका आवाज नहीं आ रहा है.
हाँ
नहीं करना.
हाँ हाँ त्यांचा आवाज नाही होता.
Yes, roll number 63.
Sorry, sir. There is network issue a little bit. Sorry, I will continue with due respect. Sir has obtained his doctoral degree in solid state physics in 2002 and possesses more than 2 decades of postgraduate teaching
Right.
and research experience. He has successfully guided 6 PhD scholars with several research scholars currently working under his supervision. His research uh, contributions are extensive and impactful, with over 120 publications in reputed national international journals and conferences proceedings. His scholarly work has received international recognition, including listing among the top 25 most cited articles worldwide in his research domain. Dr. Dole sir has also been a principal investigator for several major research projects funded by the prestigious national agencies such as UGC, DST, DAE, and IUAC, with cumulative funding exceeding rupees 40 lakhs. In addition to research, he has delivered more than 450 invited academic lectures, workshops, and extensions talk at national and international levels. He has played a significant role in academic leadership and university administration, serving as chairman, board of studies in physics, and contributing actively curriculum design, academic planning, and quality assurance initiatives. In recognition of his outstanding academic research contributions, he has been the recipient of several awards, including Rashtriya Gaurav Award, Excellent Teachers Award, and Ideal Teacher Award, conferred by Dr. Babasaheb Ambedkar Marathwada University, Chhatrapati Sambhajinagar. We are honored to benefit from academic insights and scholarly experience of such a distinguished resource person. With these words, I respectfully hand over the dais to our esteemed resource person, sir. The dais is yours, sir. Thank you.
Thank you very much for this very nice introduction. Uh, what I have done, uh, fact is that uh, whether it is useful or not, if it is useful to the society, then that is the research I do consider. And because the today's title of my talk is Advanced Materials for Futuristic Applications, Innovations and Opportunities. What are the innovations we have done, and what are the opportunities in this? Because as you know that the material, but the here the title is the advanced materials for futuristic applications. Here we are very much optimistic because the material plays the role, the very extensive, exotic, and impactful, and that role of the material is constructive, not destructive. And if that material means we are handling, for example, today this technology, all these things, okay, step by step. Today, I would like to, because here the advanced materials, what type of materials and their applications, but we people do consider that we think about the utility. Am I right? Am I audible?
Yes, sir. Yes, sir. You are audible, sir.
Yeah. Now you see uh, the others, those are working in the areas. They are working and struggling day and night, but for the societal benefit. But where we stand, that is again the important. And therefore, the rapid advancement of science and technology significantly increase the demand for high performance materials with superior properties. It is not today. Since the uh, in a stone era, okay, since then the man has been working and trying to solve the puzzles, problems, and to cross the barriers. Okay, therefore, the advanced materials, and these are advanced materials, namely nanomaterials, functional composites, metamaterials, and smart materials, are revolutionary. So these are the revolutionizing. This revolutionizing means they playing the very vital role in a various industries. So there is the revolution regarding this one. From so again here the across the globe and including India, we are facing the problem, that is the how to store the energy storage to biomedical applications, and the materials show the unique mechanical, electrical, optical, and chemical properties, making them essential for next generation technologies. Okay, now you see the Michael Faraday and though these scientists work on the electricity, and now you see we have been using that the copper wire as a good electrical conductor, copper. But can we replace? Still, we we are using the same. This presentation outlines the latest innovations in advanced materials, focusing on emerging trends, fabrication techniques, and exotic, exotic, very, very advanced novel applications. Now, the another important thing is that the commercialization and industrial adoption opportunities can ad- address the scalability, cost effectiveness, and sustainability challenges. So, more importantly, the commercialization and it it may address that the if you develop any innovative material product, then what are the opportunities, and the developed product is a cost effective or not. If it is not cost effective, then there is demand, but due to the cost, the common man cannot sustain that one, cannot purchase that one. Therefore, it is also the commercialization and cost effectiveness both are playing important role. The more importantly, the main topics covered including materials, that is the graphene, transition, and emergence. Okay. For energy storage, photocatalysis, flexible electronics, and sensors. So, photocatalysis and electrons, nanocomposites, and hybrid materials for enhanced mechanical and thermal performance. Metamaterials for photonics, electromagnetic wave manipulation, and stealth applications. Bio-inspired and smart materials for biomedical, self-healing, and adaptive technologies. Sustainability challenges and the role of advanced materials in achieving a greener future. Okay. Now you see the nanospheres and clusters, that is the zero dimensional. Okay. So zero dimensional nanospheres and clusters, quantum dots, fullerenes, and gold nanoparticles. These are the zero dimensional. Okay. One dimensional, that is the nanotube, nanowires, okay, carbon nanotubes, metal nanorods, okay, one dimensional rods, and because these are the materials classified in zero dimension, one dimension, and two dimension, thin film plates, layered structures. Okay, thin film, layered structures, layered nano materials, graphene sheets. Okay, and three-dimensional bulk nanomaterials, polycrystals. Okay, these are the means here. Okay, and nanotubes, as I mentioned that one, the nanowires and nanotubes are one-dimensional, thin films, plates, and layer structures, polycrystalline, liposome, and dendrimer. Okay, polycrystals, three-dimensional. Means zero-dimensional nanospheres and clusters. So the question is there, if we are talking about the advanced materials, then what is this? Advanced materials refer to engineered substances with superior properties to conventional materials, making them suitable for high performance applications. Okay. across various speeds. These materials exhibit exceptional characteristics such as high mechanical strength, electrical conductivity, thermal stability, optical tunability, and chemical reactivity. So these materials exhibit exceptional characteristics such as which advanced materials, high performance, okay, means that era over we have to engineer the materials with superior properties. Advanced materials, this term is referred to engineered, the advanced engineered the materials, substances with superior properties to conventional materials. Okay, conventional materials, superior properties to conventional materials, making them suitable to high performance applications. Now these materials outline, these materials reflect the exceptional characteristics, and these are the high mechanical strength, electrical conductivity, thermal conductivity, chemical reactivity, optical tunability. These properties, these characteristics, okay, these materials have. Now here, then these characteristics, which material carry these characteristics, carry the following materials, namely graphene, M-chains, and they have the high entropy alloys, metal organic frameworks, MOF, metal organic frameworks, perovskites, and bio-inspired materials. Okay, these are the materials, they have the high performance applications with the superior properties to the conventional materials. Okay, so therefore these materials are outlined. It means the high entropy metal organic frameworks again. So their unique properties enable their use in energy storage, environmental remediation. Their unique properties enable their use in energy storage, environmental remediation, okay, use in energy storage. These materials and their applications and use in the energy storage, okay, they have and they show the unique properties, and their unique properties enable their use in energy storage, environmental remediation, biomedical applications, and next generation electronics, for the next generation electronics. Now emerging trends in advanced materials. So two-dimensional materials, that is the graphene, M-chains, and transition metal. Okay, here the high electrical thermal conductivity, mechanical strength, and surface area, and the applications of these materials are energy storage, flexible electronics, and sensor. Now sensors, nanocomposites, and hybrid materials, combining nanomaterials with polymers, metals, or ceramics for tailored properties, and their applications, structural materials, coatings, and biomedical uses. Now metamaterial engineers to manipulate electromagnetic waves, negative, and it has the negative refractive index. Photonics means these metamaterials used in case of wireless communication and photonics, okay, and clockings. The smart and bio-inspired materials, self-healing, so smart and bio-inspired, shape memory and biomimetic materials inspired by nature, wearable technology, robotics, and medical devices. This is the classification, and as we know that the oxides means material class here, and this is the which type of material. Okay, now it is shown here. These are the examples. So oxides, namely TiO2, zinc oxide, iron oxide, tin oxide, aluminum oxide, copper oxide, molybdenum trioxide. Okay, these are the oxides, and these metals also play important. Sulfides, MOS2 means molybdenum disulfide, tungsten disulfide, zinc sulfide, cadmium sulfide, disulfide, copper sulfide, lead sulfide. These are the sulfides because here O in oxides, O at the end of the chemical, and here S selenides, and this is the molybdenum diselenide, tungsten diselenide, zinc selenide, cadmium selenide. Okay, these are the examples. Tellurides means this is the telluride, bismuth telluride, then the antimony telluride, molybdenum telluride, ditelluride, dientra. Now nitrides, boron nitride, gallium nitride, aluminum nitride, carbides, TiC, silicon carbide, tungsten carbide, zirconium carbide, all these, okay. And phosphides, that is the gallium phosphide, indium phosphide, zinc phosphide, diphosphide. This is the copper phosphide. So dimensionality again plays a very important role in this case. Now, zero-dimensional quantum dots, as I mentioned, cadmium selenide, lead sulfide, and zinc oxide, fullerenes, C60, C70, metal nanoparticles, carbon dots. Means the quantum dots, that is the cadmium selenide, then the bismuth sulfide and zinc oxide, these metals show nanoparticles with all dimensions confined at the nanoscale, leading to unique optical and electronic properties. One dimensional, as I outlined and given the examples, wires and tubes. These are the nanorods, nanowires, and tubes are the carbon nanotubes are the one-dimensional materials. Materials with one dimension, significantly larger than the other two, exhibiting high aspect ratios and excellent charge transport properties. Two-dimensional graphene, MGens. These are the atomically thin materials with strong in plane bonding and weak van der Waals interactions between layers, leading to exceptional mechanical, optical, and electronic properties. Three-dimensional metal organic framework, as I mentioned that one, covalent organic frameworks, perovskites and bulk materials and metals, bulk metals, metals with all three dimensions extending in space, providing structural integrity and diverse functionalities for various applications. Now here we talk about zero dimension. One dimension means zero dimension, that is the quantum dots, okay, and one dimension, that is the nanotube, nanowires, two dimension, thin films, okay, all these, and the clusters, okay. Now you see we talk about all these points, and now the main and important aspect, still there is a question mark. How these materials we classified to 0 to 3 dimension, okay, and but how one can synthesize. So materials we successfully classified, but if we are not able to synthesize, then what is the utility? What is the application? What are the applications of this? And therefore, here we successfully synthesize these materials using the following routes, and that is the co-precipitation, chemical bath, CVD, then the Silar, that is the successive ionic layer adsorption and reaction. Sol-gel method, chemical vapor, CVD, EDM, that is the ECD, electrochemical, electrophoretic, Hamas method, and hydrothermal method. Using these methods, we can synthesize the materials. So here is the description of the co-precipitation method. It involves the chemical precipitation of zinc ions using a precipitating agent, that is the sodium hydroxide, and NH4OH. The reaction leads to the formation of zinc hydroxyl group, which decomposes into ZNO, this one. Now ZNO synthesis using co-precipitation method, that is the precipitation of zinc solution dissolved in zinc nitrate, dinitrate in deionized water, this precipitation of. Now addition of precipitating agent, that is these are the precipitating agent under stirring, then the formation of zinc hydroxyl precipitate, that is the white PPT gets here. Now aging and washing, it settle, wash with ethanol and water, that is the distilled water. Drying and calcination, this heat treatment given to in the range 400 to 600 to obtain ZNO nanoparticles. And this is the route how to synthesize. Now you see this zinc chloride, zinc dichloride, weighed first, and then in means deionized water, okay, here. Now mixing the solution by stirring for 30 minutes on magnetic stirrer. Here is this piece is the in the beaker, magnetic, this is the stirrer, okay, and here is this, it is on the hot plate and magnetic stirrer, okay. Now again pour into this beaker, that is the NaOH solution poured dropwise into prepared zinc chloride homogeneous solution. Now here what we obtained here, obtained precipitates here, we got the precipitates and we washed with several times with ethanol and deionized water. Now again what dried precipitate here, we got the precipitate but it was the wet precipitate. Now it is dried where annealed at 500 degrees Celsius. Okay. Now you see this zinc chloride and this NaOH. Okay. Now adding NaOH in deionized water. Okay. Here also deionized water, zinc means sodium hydroxide and zinc dichloride. Now here it is homogeneously, we have to get the homogeneous solution, therefore magnetic stirrer, here is the magnetic stirrer. Now both the solutions now in this beaker poured, okay, and therefore the NaOH solution poured dropwise into prepared here zinc chloride, okay, and homogeneous solution obtained here. And after getting the precipitate, it is also washed several times with deionized water and that dried up to 400 to 500 degrees Celsius. And then we got the white ZNO nanoparticles. ZNO nanoparticles. See, these are the ZNO nanoparticles. Now, because here ZNO nanoparticles, quantum dots, if the crystallite size below 10 nanometer, from 0 above 0 to below 10 nanometer, it is a quantum dot. And we successfully synthesized the ZNO, zinc oxide, using the co-precipitation. Now, what is the chemical bath deposition? Now, this chemical bath deposition, this method is being used to synthesize the one-dimensional and two-dimensional, mainly the nanotubes, means carbon nanotubes, nanowires. These are the one-dimensional, and thin films, two-dimensional. Okay, plates and thin films. Now, example TiO2, thin films. Now, the controlled chemical reaction in an aqueous solution forms a thin film on a substrate. The flowchart of this method is outlined here. Point-wise precipitation, that the preparation of solution, dissolve TiCl4 means this titanium tetrachloride or titanium sulfate, disulfate in water. Okay. Addition of complexing agent, that is the NH4OH to control pH. Now, substrate immersion, deep glass or FTO substrate. Deposition process here outlined, and that is the TiO2 nanoparticles nucleate and glow, that is a grow. Okay, deposition process here, TiO2 nanoparticles nucleate and grow. Now annealing and characterization. So here the phase change if we heat up to 500 degrees Celsius. Now this schematic outlines that the synthesis route. Okay, and here the beaker and the this substrate inside the beaker, and it is deep, means it is under the water, means inside the beaker. This substrate, water bath, reaction bath, TI2 means thin film. Okay, on that. O2 means here unreacted ions. Okay. Glass substrate, that is this one. This is in what? In solution. Temperature controller is here, and how to control the RPM. Successive, that is the another. Hello. Am I audible? Yes.
Yes,
Yes,
sir.
sir. Yes, sir.
Is there any problem? Are you getting bored? Hello. Hello. Do you know Scylla technique? How many are from science faculty? It is question for participants. So how many are from science? All are from science faculty?
No, sir, I am from social sciences.
Yeah. How many are there? Please.
Sir, I am from chemistry
I
background.
am from science faculty, sir.
Okay. Now, is it understandable? Can you
Yes,
understand
sir.
this?
Yes,
Yes,
sir.
sir, yes, sir.
Yes, sir. Yes, sir.
Okay, because you are just sitting and listening. So if there is no participation, there is no discussion. Just I am going slide by slide, and you are listening. But fact is that your participation is also I am expecting in this case. Okay. Now after this we will go, because this is the experimental part, not the theoretical part, and how to synthesize the materials, because the most of the students and the professors, they are also working in this field, and how to synthesize the material, that is the challenging job. But here I described and elaborated some techniques in this respect, and this is the method. Now this is the cellular technique. See here, the first what we have taken, the here is the water, how to clean, but the material cationic precursor, that is the Ti2 plus means Ti2. These are the ions. This is the N2 ion. Okay, minus. Now this is the cationic, means how to. And these are the substrates. Now this is the one substrate, but first we have to dip this one in first beaker, then the another beaker, means we have to again here after dipping into this solution, then we have to clean it, then some particles deposited here, again on this substrate, again deposited particles, again dip in anionic precursor, and then again the diff means clean using the H2O water, and then remove. This initially there was nothing, but see after this, these are the steps. This is the one substrate, not the five substrates. Okay, because in first four beaker we have to dip. Okay, and therefore the first it is the very clean substrate, and then after the dipping into the last one, how many particles deposited on the substrate shown here. This is the Sol-Gel route, and here the material we can synthesize using this method, that is the Sol-Gel method, and this method is applicable for 0, 1 and 2 dimensional materials. Okay, in TiO2 we can synthesize. Now this is the flow chart of this method, how to, and this is the flow chart. Now you see, then the CVD, this is again here the weakened titanium nuts and nanoparticles we can synthesize, and this is applicable for 1 and 2 dimensional. Now electrochemical deposition method, again for this, and this is the electrochemical deposition method. Okay, electrochemical. Now more means this again very important method. and the graphene oxide we can synthesize, and here is this one. Okay, electrophoretic deposition method. Using this we can synthesize, and here how one can deposit the materials. Okay, now Hammer's method, this is also important, and the potassium permanganate we can sulfuric, uh, that is the sulfuric acid H2SO4, we can, okay, here synthesize these materials, and these are the means the flow chart, and this is the procedure of this method. Okay, and see, very important, the step by step we have to go. Now the last method, that is the hydrothermal method, and this method can be used for the synthesizing these 0, 1, 2, 3 dimensional materials. And this is very important technique. And here we can synthesize the cobalt oxide, quantum dots, zinc oxide, nano zinc oxide and zinc sulfide, nano wires, graphene oxide nano sheets, two-dimensional, bismuth oxide nano sheets, manganese oxide nanoflex, and ZNS nanospheres and nanocubes. We can, now you see here the cube again. Here the three-dimensional materials, so we can. Now the principle of this method is given, and that is the autoclave we use to crystallize the materials, and the precipitation precursors, zinc nitrate in aqueous solution, heat up to this 120, 150 degrees Celsius, and then the zinc oxide nanorods, formation of this one, cooling, washing and drying, that is the purified product. And now this is the hydrothermal method. Here very interesting, and we have to use the autoclave here and pour the solution, and then give the heat up to 160 degrees Celsius. Then the creation here just like cooker, but it is very special device, and then we can synthesize the nano, means nano wires, again nano particles of films. Okay, so here as why this method is being used. Okay, now it is a advanced and highly effective technique for synthesizing 0 to 3-dimensional nanomaterials, and due to precipitation, the chemical vapor deposition and physical vapor deposition. Below, these are the reasons why the hydrothermal method is superior than the above mentioned 8 methods. So it has the wide applicability for different nanostructures, means no limitations. You can employ this method to synthesize the 0 to 3-dimensional, but for the other methods, there are the limitations. Now, this one-dimensional nanowires anisotropic growth in hydrothermal conditions permits the formation of well-aligned nanowires, nanorods, or nanotubes. Okay, and for this is very interesting, because the thin films and films and sheets can be synthesized, and that is classified into two-dimensional. Okay, now the here the hierarchical structures, that is the three-dimensional. It the flower-like, cube-like. Okay, and these are the materials we can. Now, precise morphology and size control. So the temperature up to 300 degrees Celsius, pressure, reaction time, and precursor concentration can't be precisely controlled, leading to highly uniform and reproducible nanostructures. Now it facilitates the anisotropic growth of nanostructures. Okay, crucial for advanced material applications. And now this again the very important uh, is what is the important of this method? The importance of this method is eco-friendly and scalable. So you can water or other green solvents, making it an environmentally friendly process compared to soldier, which may require toxic organic solvents or chemical vapor deposition or physical vapor deposition, which requires high vacuum and hazardous gases. But in this case, there is a scalability. Means scalability is excellent, allowing large-scale production of nanomaterials with low cost and high yield. This meant high crystallinity and purity. This method gives that one the hydrothermal promotes defect-free crystal growth due to this low reaction kinetics leading to highly crystalline structures. Now, in a contrast, soldier and compression method often require post-annealing, which may introduce defects or impurities. Now, synthesis of complex and multi-component nanomaterials. Okay, it allows for doping, heterostructure formation, and composite synthesis in a single step. Okay. Now, the example of this is the tungsten carbide based EMnO2 nickel doped that is the CO3O4 nanocomposites can be synthesized without multiple processing step. Now, energy efficient and low processing temperature. It works at relatively low temperature compared to chemical vapor deposition, and sir, hello, बर बर त्याच्याही जवळ दिलं तरी त्याला बोलून घ्या किंवा मी सांगतो कोणाशी नाही 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 अजित ना ना सर सर मी निवांतपणे बोल मीटिंग एक मीटिंग चालू आहे मी निवांत बोलतो ओके मी लावतो ओके ओके so reduces energy consumption while still enabling high quality material formation. Okay, this method. Energy efficient and low processing temperature here. So control surface chemistry for functional applications. Hydrothermal conditions allow for precise control over surface functionalization. Okay, so this which is important for supercapacitors. So this method is useful for synthesizing the material of supercapacitor material. Okay, that is the charge storage. Photocatalysis increase active surface sites. Membristors, that is the optimized defect engineering. Okay, and photosensitivity applications, enhanced light absorption. Now prepare nanomaterials for the application of photocatalytic activity, antibacterial activity, sensor, photodetector, and supercapacitor. Okay, this means nanomaterials for the application of these following means photodetector, sensor, antibacterial activity, and photocatalytic activity, and supercapacitor. Okay, these materials, the prepared materials means the material prepared from the material prepared using this method can be used for these applications. Okay. So here the iron doped bismuth oxide, and the paper was published in the results in chemistry. Its impact factor was 2.3. So this is the crystallographic study of the synthesized pure bismuth oxide materials, and now here you see the lattice parameters and all these. This is the X-ray diffraction. These are the patterns. Okay, and this is the volume, crystallite size, dislocation density, microstrain, and stocking fault of pristine and iron doped bismuth oxide samples. Okay, so here enhance means you see here is the means enhancement up to this, and here is the volume also in volume enhance if the uh, percentage of the iron enhanced in the host. See here the percentage enhanced, then the volume increased and crystallized size decreased. Okay, volume increased but crystallite size decreased, means it is inversely proportional. Dislocation density here up to this increased, microstrain here increased and then decreased, and stocking fault. Okay, here up to this increased and then decreased, means the 0.5% iron doped bismuth oxide. So up to this, and then after this, it is reversed. These are the same images. I means this is the FE same. Okay, that is the field emission scanning electron microscope of these materials, and see here A pure material. See, it is just like the little bit here. It shows the rod-like structure you see here, images. Then the doping of this iron. This is B. Now after doping, you see again it converts into sheets here again, and means this is C. Here you see, and here again she long elongated rod, and at the surface rods and sheets. See, this is the Fe same of iron doped. Then the photocatalytic activity of this, and here is photo degradation of methylene blue dye by pure and iron dope, pure sample 0 minute. How much time it takes? That is 180, and this peak. Now you see, this is for pure. Here is the time is reduced now, means you see the height of this decreased, and for this again, now you see this is decreased. Dye, photo degradation. Now this plot of time versus C by C 0 and plot of time versus log and variation of the relative concentration of methylene blue dye solution under visible light irradiation in the presence of pure and these nanorods over the cycles. Now C by C0 this plot for pure then 0.3% iron doped bismuth oxide. Okay, now this is red 0.3, 0.5, points 0.5 blue and 0.7 this. Okay. Now this is the case. Here the photo degradation efficiency pseudo first order rate constant of the iron substituted bismuth oxide samples. And now this is the pseudo first order rate for this pseudo, that is the photocatalytic efficiency pseudo rate constant in the photocatalytic efficiency cycle 1, cycle 2, cycle 3, cycle 4 and cycle 5. Here the same thing for first, second, third, fifth, fourth and fifth cycles of the materials. And that is now antimicrobial activity. Now you see here, this is 0.3. No, here for 0.3, that is and for other samples, this activity means the material covers, means infected, but for this, no infection, no coverage. Okay, again, for this is pure, here is this pure, but against bacillus bacteria and aspergillus flaws fungi. Okay, now for this, what is this diameter of zone inhibition in millimeter? So for 0.5, this diameter is higher. Okay, now concentration of this and for 0.5 iron doped bismuth oxide, that is 23, means which bacillus bacteria and aspergillus plus fungi are used here, and we got the area at this. Okay, means 0.5 it is more covered, and for this again here more cover. You see here means how much it is covered here, this much. Okay, and here this see, and here little less, but here you see here 0.5. Now graphene oxide based iron doped bismuth, more interesting, and this paper was published in this. Okay, and the crystallographic study, and these are the parameters which we calculated after using this geo based. These are and that is also percentage wise, and calculated the volume, crystallized size, dislocation density, microstrain, all these. Okay, and here is the change. हॅलो सर, नमस्कार. मी लेक्चर मध्ये जरा आपण बोलू ना, मी लावतो. हा 2च्या नंतर. हो 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 Now you see the volume enhances up to 0.5 and then again decreased. So here and crystallized size again increased and then decreased up to 0.3, and dislocation density here first then decreased and then again increased and then decreased. Here is the dislocation density because depends on the synthesis, and these are the stocking pods. Now you see these are the micrographs, okay, of as prepared material. Now these are the time evaluation spectra of Congo, red azo dye degradation, photocatalytic activity, and pure this one, then the plot of time variation of these materials, okay. Plot of time versus log variation of this one, the cycles and all these we calculated. So this is the work which carried out in the laboratories using the different dyes, that is the methylene blue, then the EMO, and then the MB okay. How much the effects of various scavengers on the photocatalytic degradation efficiency shown here, the effect of these various scavengers, and that is in this percentage, okay. And now you see this enhanced different scavengers here again. For this it is means 0.7 GO and 0.7% iron. It is highest for this, and for pure decreased. Now these are the cases here. Different materials we synthesized in the laboratory, and that is the advanced material research laboratory materials, and that is geo-based tin iron co-doped bismuth oxide nanocomposites. This work has been published in the Journal of Energy Storage, and its impact factor is 9.4. Now you see the work which I carried out successfully in the laboratory, and the topic of this was given to the my one of the research scholar, uh, Mr. Vijay Mane, and then we synthesize successfully and characterize using the following techniques. This is the XRD of this, and these are the samples. Okay, now you see these are the FE same of the as prepared material, and here you see the clear cut sheet. Okay, now you see this one, and this is the cyclic voltammetry curves of pure, then the tin iron codope, and then the geo pure and geo 5%, all this. And now you see this cusp here, we can find out the the efficiency of the material, and you see here the uh, galvanometric, galvanic charge discharge curves of all synthesized samples, 0.1 RNS per gram, and the calculated capacitance of using this one we calculated the specific capacitance, and that is I that is for this 137.58, okay. This per gram, that is farad per gram, and the solution resistance also calculated, and the efficiency means specific capacitance we got here, that is after doping means addition and doping of this one. Now you see 1000 302.5. Okay, this is this one. And resistance, that is the charge transfer resistance, here decreased. Now this plot, cyclic stability and Nyquist plot, Coulombic efficiency of synthesized samples. Okay, and now you see capacitance retention and Coulombic efficiency also we have calculated here, and that is the case. Now titanium dope cobalt oxide nanoparticles, and this work also published in Materials to the Communication Impact Factor 3.7, and these are the Scopus Index papers, XRD of the materials. Okay, and these are the means the materials and XRD parameters of as prepared materials. And now you see very interesting thing. See here the material, the FIP shows the what the micrographs reflects that the surface morphology. See here the material, this is the nano rod. Here you see the rods. See, are these states. E is the TCO7. Means here the cobalt oxide titanium doped. Okay, titanium doped cobalt oxide samples. See here in E, nanorods, length in nanometer 2166 and thickness is 68. Means two-dimensional nanomaterials we successfully synthesized. These are the photocatalytic activity, time study, then in 0 to 20 minutes, the cycle MB degeneration spectra of samples and for all the samples. Okay. Now degradation efficiency and pseudo first order rate constant we calculated for this, and that is the case here. Degradation efficiency for this is, and it is the highest for TCO3. Now cobalt based titanium dope cobalt oxide nanocomposites. This paper, this work has been published in Ceramic International with means impact factor 5.1. And now you see here degradation product. We got here the material and XRD here. Oh, it is very interesting again. For this, we successfully synthesized and we got the micrographs. See here the slab-like sheets. Okay, two-dimensional materials, films and sheets. See, 200 nanometer. We got the length of this is 2160 nanometer. Thickness is lesser, but the length is higher. Photocatalytic activity, again here the photo degradation of MO and MB mixed dye by GPCO. These are the material codes. Effect of a radical scavenger addition on photo degradation of MB and MO mixed dye under sunlight over this. The first order pseudo rate constant and photocatalytic efficiency of GPCO. Okay, and it is calculated on this port. Okay, these samples. Now graphene oxide based nickel doped MnO2. This is again the interesting work. Here is the reference electrode. And this is the working electrode. And this is the counter electrode. Means this graphite is the counter and this is the working electrode. That is the MnO2 nickel doped, and this is the reference electrode. Now you see graphical abstract of this is given here. X-ray diffraction patterns of as paper samples and its structural parameters outlined here. Oh, see here, very interesting micrographs obtained of these materials, just like cube-like structures. This is again the cyclic voltammetry. Now calculate the efficiency of the material. Then this is the charge discharge curves of all samples. Okay, and charging and discharging process we followed here. Charging and then means this is the charging and discharging. Charging and discharging rate means discharging enhanced. You see here. Here is the charging and then discharged. Means, okay, as synthesized samples, electrochemical impedance spectroscopy and the specific capacitance of all synthesized nanocomposite samples, specific capacitance, that is the farad per gram at scan rate, this one. So here is the increased, then decreased. Okay, charge transfer resistance increased for this. Reduced graphene oxide iron doped alpha MnO2. So here the structures of this, and you see the nanowires. These are the X-ray diffractometers, diffraction patterns. And these are the micrographs of the samples. The particle size and aspect ratio of all synthesized materials is given here. And these are the cyclic CV of the materials. Then galvanometric galvano charge discharge curves of the samples. You see, as I mentioned earlier also, these are the, okay. Now tungsten decorated reduced graphene oxide based iron nickel co-doped MnO2. Now this work also was published in Journal of Material Science and Materials in Electronics. 9.4 impact factor. Here you see the nanorods. So this is the intensity, the figure XRD patterns of the TGO, MnO2 and the iron doped, all this, and here you see the XRD pattern and its structural parameters also outlined here. These are the specific capacitance and it is also enhanced here, you see. Now, bilayer N-doped tungsten modified GO hybrid composites. And this work was published in Journal of Material Science and Materials in Electronics in impact factor. with impact factor 9.4. Now see here. Oh, here are the calculated crystallographic parameters of the materials, and very amazing. You see, the material shows the sheets here, which we synthesized, and these are the galvanostatic and cyclovoltammetry plots, and this is the galvanostatic charge discharge. Charging rate is lesser than the discharging. Okay, therefore it goes like this and then slowly come. Here is the current density, specific capacitors, charge transfer resistance and solution resistance of these materials, electrochemical impedance of the materials. Now, what is the future scope? Future scope of advanced materials, graphene functionalization and its applications. Okay. Now, the two-dimensional nanomaterial with exceptional electrochemical, electrical, thermal, and mechanical properties is a key focus in cutting-edge nanotechnology research. The functionalization of graphene by introducing heteroatoms, surface modifications, or hybrid structures enhances its applicability in various fields, including biomedical, engineering, photocapacitors, solar cells, and water purification. Below is the future scope of graphene functionalization in these domains. Now, graphene functionalization for biomedical engineering. So these are the derivatives, that is the GO and functionalized graphene exhibit biocompatibility, antibacterial properties, high surface area, and more interesting is the excellent electrical conductivity, making them promising materials for biomedical applications. So these materials can be used for the drug delivery, that is the functionalized graphene-based nano carriers can be used for targeted drug delivery and controlled release. Graphene conjugated with polyethylene glycol or chistosan can enhance biocompatibility, biosensors, and diagnostics. Graphene-based electrochemical biosensors for real-time detection and diseases, cancer, diabetes, viruses, etc. Means graphene-based electrochemical biosensors. Okay. Now DNA functionalized graphene for genetic sensing applications, tissue engineering, and regenerative medicine. Graphene-based scaffolds for bone, neural, and muscle regeneration due to their excellent mechanical strength and conductivity. Functionalized graphene coatings for biocompatible implants, antibacterial and antiviral coatings. Graphene oxide functionalized with silver, Ag, zinc oxide, ZnO, or copper, Cu, for antimicrobial coatings in hospitals on medical devices. These are the applications of the materials and the future scope of the graphene quantum dot hybrid for enhanced photo charging. So combining graphene with pesquite quantum dots or carbon dots can boost light absorption and charge separation. So this is the future scope of graphene quantum dot and graphene MGen composites for graphene performance electrodes. Now MGen is, that is the titanium tetra means tri-titanium, C2TX means carbide, means carbon, and this and graphene hybrids can improve capacity, energy storage, and cycling stability. Graphene-based flexible and variable photocapacitors, we can, that's photo supercapacitors. Functionalized graphene can be integrated into flexible supercapacitor devices for variable electronics. Graphene as a transparent electrode for light absorption enhancement. So indium tin oxide for transparent electrodes, making visible, transparent, and efficient photocapacitors. Now this graphene functionalization for solar cells. Now it is been interesting. Solar cells, okay. Solar cells is interesting nowadays. The India is also using the solar cells, but how one can fabricate, design, okay. That is important. Graphene functionalization. So graphene's high electrical conductivity and tunable work function make it an ideal material for next generation photovoltaic devices. Okay, this graphene functionalization for means it is being used, and this graphene is very important for next generation photovoltaic devices. Functionalization of graphene enhances the electron mobility, charge separation, and light absorption, leading to a high efficiency solar cells. So leading to high efficiency solar cells. So enhances electron mobility, charge separation, and light absorption. Means of functionalization of graphene increases the electron mobility, charge separation, and light absorption. Means it enhances the high efficiency solar cells. So graphene perovskite solar cells, PSC, perovskite solar cells, that is GPSC, graphene doped perovskite solar cells can improve electron transport and enhance efficiency. Functionalize graphene as a whole transport layers and electron transport layers in PSC can lead to stable and high performance solar cells. Now, more importantly, graphene in tandem solar cells. So, graphene silicon hybrid solar cells for enhanced stability and light absorption. Graphene organic hybrid solar cells for cost effective. Graphene organic, it is inflexible photovoltaics. Now, graphene-based transparent conducting electrodes, TCES, transparent conducting electrodes. Functionalized graphene can replace ITO-based electrodes for lightweight, bendable, and cost-effective solar cells. Quantum, that is the graphene quantum dots for light harvesting. Graphene quantum dots can be used as sensitizers in dye sensitized solar cells. Dye sensitized solar cells, and this as sanitizers. No, sorry, as sensitizers. Graphene quantum dots can be used as sensitizers in dye sensitized solar cells, and it may improve efficiency. Graphene functionalization for water purification. These materials can be used for water, means graphene functionalized can be used for water purification. Graphene based nanomaterials often and offer excellent adsorption, offer excellent adsorption, filtration, and antibacterial properties, making them ideal for advanced water purification technologies. Okay. Graphene based nanomaterials. Excellent adsorption, filtration, and antibacterial properties. Graphene-based nanofiltration membranes, functionalized graphene membranes with nanopores for efficient desalination and removal of heavy metal. Graphene enabled photocatalysis for wastewater treatment. Graphene TiO2 or graphene ZNO composites for degradation of organic pollutants using solar-driven photocatalysis. Graphene as an adsorbent for heavy metal removal. Graphene is this graphene, functionalized graphene with carboxyl or hydroxyl groups for enhanced adsorption of lead, arsenic, and mercury. Graphene-based antibacterial coatings for water filters. Okay, antibacterial coatings for water filter. Graphene membranes functionalized with silver nanoparticles for bacterial inactivation in water filters, self-cleaning and anti-fouling graphene-based filters, graphene membranes with super hydrophobic and antibacterial properties can prevent biofouling and enhanced filtration longevity. So self-cleaning and anti-fouling graphene-based filters. We can synthesize, we can fabricate, we can design the graphene-based filters, anti-fouling. Now, this is the here what we have, as I described whole talk here, because we have successfully synthesized the materials, not only the laboratory work we successfully completed, but we published the papers in high impact factor journal. And if you go on the website, just means on Google Scholar, and just edit the B and Dole, you will get the things. But what we have done, and whether it is useful for society or not, and now you see, in my laboratory, we successfully synthesize the nano ink using the graphene, okay, RGO, and this is the A4 size paper, and on that these are the lines which I drawn, and if you pour the water on this, the record, lines will not, ink will not disperse, means. And as I mentioned that one, the cost effectiveness should be there, and for this work Means I submitted for the patent and I got the patent on this, and that patent published on May and granted on 25. Okay. Means after the 1 year in April 2025, we got the means the patent granted. So this is the work I have done. Now the some people again, this is the stamp ink, not stamp. Stamp ink also we successfully synthesized. This is the ink, and now I will show you. In my hand, कोरा कागद आहे का? Okay. Time? दोन वाजेपर्यंत. ओके. 2 तास होत आहेत ना. आपण 12ला सुरू केलं. किती वाजता आहे? नाही किती करायचंय? बर बर. Now you see, is it visible? Hello.
Yes, sir. It's visible. It's visible.
Yes.
As I described that one, because you see, this is the pen, fountain pen, and this is in my hand. And you see, what we prepared, that nano ink in the laboratory. And as I described that one, we got the patent, granted patent on this. Patent granted in April 2025. Now this is the pen, and I draw the line before you now using my pen. Now you see, this is the pen in my hand, and I write on this pen, on this paper. Now you can see. Is it visible?
Yes, sir.
Right? Okay. Now you see, this is the yum, you see yum, TTC. Okay. I wrote here TTC. Now I wrote, now I pour the water. Okay. What I have done, have you seen? Anybody can tell me?
Yes, I.
What I have done, I wrote the MMTTC, okay, using my pen, that is the nano ink, and then I pour the water, okay. Now you see before you, can you see? Wait, right? I poured the water on this, correct? But record is there as it is. Is it correct? Is it visible?
Yes, sir.
Now you see?
Yes, sir. It's visible.
Yes, you see now again I drop the water on this. Right? Is it visible?
Yes.
Right? Record is there. Means your letters not rubbed. Okay. Means C. As it is, lines are there. Correct? Means here this ink I successfully synthesized in the Advanced Metal Research Laboratory, Department of Physics, Dr. Babasaheb Ambedkar Marathwada University, Chhatrapati Sambhaji Nagar. And what are the applications? As I mentioned, that one, the GO, and using the RGO, I successfully synthesized. And the life of this means how many years old this pen? This is the 6 years. Okay, the in 2019 I purchased this pen. Since then I have been using this pen. Because as I mentioned, that one, the material which we synthesize, it should be the cost effective, and the what are the means what are the applications of the as prepared material as I described. The one thing, the another thing, as prepared the nano ink, how is it different from the available ink? Yeah, available market ink. Okay, so I would like to describe the characteristic of this ink, because this is a we synthesized and developed this product in the Department of Physics, Dr. Babasaheb Ambedkar Marathwada University. This is chemical free ink. This is a if you write, this is a waterproof ink. Third, fourth, the surface area to volume ratio is a large than the available commercial ink. If the surface area to volume ratio is large, again, this is the sixth one is, as I mentioned, that one, but the more means surface area to volume ratio is large, then the this is the chemical free ink. If it is chemical free ink, this seventh is non-hazardous. Eighth, it is synthesized using the sugarcane bagasse. Sugarcane bagasse means that material one cannot use, but we use, and therefore it is more useful to the farmer also. Okay. 10th means if you purchase the pens, you are not creating any hazardous material and you are not destructing the nature, because once you purchase the pen, as I mentioned that one, this is the 6 years old pen, okay, and since then I have been using, means the here is the repeatability, I mean the recycling, but the pen and means only you have to use the ink, not the purchase the pen again and again. And for developing the pen, how much the company destruct the material and nature. So for constructing one pen, near about the 3 kg garbage the company generates, yeah, creates. Here, once you purchase that pen, you can reuse and reuse, not means the another the creating the hazardous material. Therefore, here is the repeatability, yeah, reproducibility, and ink from the sugarcane bagasse means reproduce. And what is the science? Now, I would like to share that idea, reproducibility. Reproducibility means science depends, science creates, science is nothing but the synthesized material. Once you prepared and again you are not capable to prepare that one, then that is not science. Science believes, science has the facets, science has the characteristics, science has the properties which you can regenerate, you can reproduce. Means reproducibility is the main aspect of the science, and which I have done that one. Now see here, the more importantly, using the sugarcane bagasse, we developed the product, and that product got the patent in granted patent in 2025. Means the societal aspect, here we have to consider the what you have done that should be beneficial to the society, to the nation, and what we have done that is useful to this society. My my uh, emphasis was on that, because we have developed the materials and you people also gone through the lecture and you listen that one carefully. But whether what we are doing, okay, whether it is useful to the society or not. And in my laboratory, in the advanced materials research laboratory, at this very small scale, we develop the product and that is useful. Now I would like to share that, because I have been working as a director, board of examination and evaluation, Dr. Babasaheb Ambedkar Marathwada University, and I use this pen for signing on all documents, and I have not purchased the another pen and ink from the market, but I am using this pen and as own prepared ink for the signing all the documents. Now you can understand. Means this pen, I have the two pens, and I'm using and not purchasing the another pen from the market, and ink also. Now, as I mentioned that one, because for all the documents I sign using these two pens, it means this is the useful to this society, and as I shown that one, the record cannot break. Now it is as it is here. You can see MMTTC. So this is the product and useful to the society. Another thing is that again we develop the and submitted that work to the patent authority, and we got the another patent on the supercapacitors. We developed the product. Again, I have the material in the form of product, and that is the nanomaterial, and it is also useful for the uh, uh, relieving for the relief of the joint pain. And the name of that product is the Vedanantak. Okay, and the so many means again that is useful for the joint pain, joint injury, and joint pain, because and here only you have to apply externally, not internally, without taking, yeah, having a single pill, yeah, tablet. You can just apply externally, you can get the relief within 13 days. Now these are the products, and generally I used to say nano product. Yeah, as we know that the allopathy is there, Ayurvedic is there, homeopathy is there, but I use nanopathy, and these are the nano product. And if we start to have this product, definitely, so external application of this product, and your pain means you get the relief from the pain. That means you can understand the potency of the product and important of the product. Now here, as I shown, these are the means, and another product is there, but I don't want to share that one. But here, as I mentioned, now the next step of this product would be the I develop this nano ink, and it is in the form of liquid. Now again I want to develop the election ink, stamp ink I developed, and I got the success in that. Then the another one is the election ink. So we are working on that one thing means, and the third form means the fourth form of this will be the printer ink. I want to develop that one, and if I get the success in this, then that will be also the useful for our country, and for this. So I share my ideas and views with you. I don't know how much beneficial for you, but what I have done, and I have completed, because I got the guidance from my guide, uh, and now, because that knowledge given to me, because I worked on the superconductivity, but I switched. I switched. I switched my research to the nanomaterials. So the knowledge got from my guide, and I share that one. But how much it is effective for you, I don't know. How much it will be useful for you, but you see the research, there is always a comma, there is a semicolon, not the full stop. You heard me very patiently. Thank you very much for listening me and listening my talk. Thank you very much. With this, I give the full stop here. But as I mentioned that one, there is always semicolon, yeah, comma. Here is the comma. Thank you. Thank you very much. If you have a question, you can ask. I do consider there is no question. Am I audible?
Yes, sir. Sir, you are audible, sir.
Yes, sir.
Now,
Sir,
if you
first
have a
question.
doubt, you can ask.
Sir, so this is roll number 65. Sir, I have one doubt. So during this photocatalytic degradation of azo dyes, so what are the degradation products?
You see, that was the bismuth oxide dope iron.
Sir, degradation of dyes. So the dye degrade into which product, sir?
Yeah. That was the methylene blue.
Okay, sir.
Methylene blue.
Okay, sir. And sir, one more thing. This during synthesis of nanoparticles in 0 dimension and 1 dimension, how does the aggregation of nanoparticles are being avoided? Like, what are the capping agents which we use, like which you were using in your synthesis part, so as to avoid the aggregation of the nanomaterials?
You see, very simple thing which you ask. There was, as I mentioned, when we synthesize the material using the co-precipitation route, then it was very hurdle and quite difficult. But when I switched on to the hydrothermal, then in case of the hydrothermal, we got the material in its pure form. And then, as I mentioned, means there also the capping agent, that is the as I shown that one, but the capping agent of that one, which I used, it was in my slide. If 1 minute, I will show you. Just a minute. Hello.
Yes, sir. Yes, sir. You are audible,
Yes,
sir.
I will show you. In the hydrothermal method, it was mentioned. Just a minute. Uh, mhm. Filtration vacuum. Okay. Mm. Mm. Just, mm. Okay. Acetic acid. Okay.
Okay, sir.
Uh, because I was thinking about the formula. Okay. Acetic acid can be one thing. Another thing, in hydrothermal, we can get that one using this one. Again, bromide can be used. Okay. acetic acid, this can be used. Okay, you see here again. So it is not shown, but these are the materials. Again, hello.
Yes, sir. Yes, sir.
Again, regarding this one, you
Correct, sir.
see
Acetic
the
acid and bromide.
you see the hydrothermal route is a more important and useful because we can get the materials uh, in the okay. So using the hydrothermal route, you can get the material and expected dimensionality and the expected form of the material, expected size of the material. Okay. So here, as I mentioned that one, and here, as I mentioned that one, the acetic acid, then the citrate, thiols, oleic, and polyethylene glycol. These are the capping agents you can use. Okay. Hello.
Yes, sir. Yes, sir. Polyethylene glycol works best, sir.
Yeah. Again, polyethylene glycol. Okay. Polyethylene glycol.
Yes, sir. Thank you, sir.
Okay. Polyvinyl also is there. Hello. Hello.
Yes, sir. Yes, sir. We are there.
Polyvinyl pyridine आणि C tab, that is the cetyl trimethyl ammonium bromide. Okay.
Okay, sir.
Thank you very much for listening.
Thank you, sir. Thank you for your presentation, sir.
Okay. हे पाणी याच्यावर टाकलं.
ओके
अरे राजू,
क्या हो गया? तो ये निकल जाओ